Tonight, we're going to talk about the universe you already recognize, the one filled with stars, galaxies, and distant light, and why your intuition about its size quietly fails the moment you rely on it. You've heard this before. It sounds simple. The universe is big, bigger than Earth, bigger than the solar system, bigger than the Milky Way. But here's what most people don't realize even when we say all of that. We are still thinking far too small. When we picture the universe, we usually picture what we can see: telescopes, images, light that has reached us. We imagine distance as something like travel, how long it would take to get there, how far away it feels. That intuition works on human scales. It collapses quietly when the scale stops cooperating. So let's anchor this immediately. The light entering your eyes right now took a fraction of a second to arrive. Light from the sun takes about 8 minutes. Light from the nearest star takes years. Light from the most distant galaxies we can observe has been travelling for almost the entire age of the universe, more than 10 billion years arriving now. Not because it is finally close, but because it has only just had enough time. This means that what we call the observable universe is not a place. It is a time limit, a boundary drawn not by distance, but by how long the universe has existed. By the end of this documentary, Stussy will understand why the universe is not just larger than what we can observe, but larger in a way that breaks the idea of observation itself. Our intuition about size, distance, and even existence will be rebuilt not to make the universe feel understandable, but to make our misunderstanding finally visible. Now let's begin. We start with something that feels stable. When we think about the universe, we usually begin with what feels visually available: stars scattered across the night sky, a hazy band of the Milky Way, photographs of galaxies taken by telescopes, arranged neatly on screens. This feels like a complete category. The universe is the collection of everything we can see when we look outward. That intuition feels reasonable because it mirrors how our everyday perception works. When we stand in a landscape, we assume that what we can see defines the space we are in. Mountains mark the horizon. Buildings define the city. Darkness limits distance. Vision feels like a boundary-setting tool. It tells us where things stop. So we bring that same logic upward. We assume that telescopes are better eyes, that more powerful instruments simply extend the same process farther out. Bigger mirrors, longer exposures, sharper detectors. The universe, in this intuition, is a very large version of a room. We are inside it, and we are slowly turning on brighter lights. This intuition does not fail immediately. In fact, it works well enough to build confidence. We learn that Earth is small compared to the solar system. The solar system is small compared to the Milky Way. The Milky Way is one galaxy among many. Each step expands scale, but the structure remains familiar. Objects sit in space. Space stretches outward. Distance is distance. The failure begins quietly, without drama, because nothing about the images tells us that the rules have changed. We see galaxies billions of light years away, arranged in deep fields. They look like objects placed far across a dark surface. Our brains register farther, not different. But this is where the problem starts. Distance in the universe does not behave like distance on Earth. Not because it is larger, but because it is entangled with time in a way our intuition is not built to handle. We need to slow this down. When light travels, it does not arrive instantly. Even at its maximum speed, it takes time to cross space. This is familiar in small ways. Thunder arrives after lightning. Radio signals lag slightly. These delays are short enough that we treat them as inconveniences, not structural features of reality. In space, delay becomes dominant. Light from the sun takes about 8 minutes to reach Earth. This already means that when we see the sun, we are not seeing it as it is, but as it was 8 minutes ago. Nothing about the image tells us this. The sun looks present, immediate, stable, but it is already history. Now we extend that same logic outward, step by step, without skipping. The nearest star beyond the sun is so distant that its light takes years to reach us. When we see it, we are seeing a version of that star from years in the past. Not metaphorically, literally. The photons entering our eyes began their journey before they arrived here. This is still manageable. Years are within human imagination, history books, memories, lifetimes. The intuition strains slightly, but it holds. Then we move to galaxies. Light from nearby galaxies takes millions of years to arrive. The image we see is a fossil record. Entire civilizations could rise and fall on Earth while that light is in transit. Still, the galaxy looks like a galaxy, a shape, a structure. The delay is invisible. As we keep going, the delay grows until it dominates everything else. Billions of years. Light that left its source when the universe itself was young. Light that has been travelling for most of cosmic history just to reach this moment. At this point, something subtle but critical happens. We are no longer looking across space. We are looking back through time. Distance has stopped being a spatial concept and has become a historical one. This is not a poetic statement. It is an observational constraint. Every image of the distant universe is a layered archive. Near objects are seen almost as they are now. Farther objects are seen as they were. The farther we look, the older the universe we're observing. There is no way around this. No instrument can bypass it. Faster travel does not help. More sensitive detectors do not help. Observation itself is limited by the age of the universe. This is where the phrase observable universe quietly enters, often without explanation. It sounds like a technical term for very far away, but that is not what it means. The observable universe is not the universe. It is the region from which light has had enough time to reach us since the universe began. That boundary is not marked by a wall, or an edge, or a drop-off in matter. It is marked by time running out. To make this feel real, we need to translate it into human experience without simplifying it away. Imagine standing in a vast, dark field at night, surrounded by people holding lanterns. Some are close. Their light reaches you quickly. Others are far. Their light takes longer to arrive. Now imagine that the lanterns only turned on at a single moment in the past. You can only see the people whose light has had time to reach you. Everyone else still exists, but their light is still on the way. In this analogy, distance and delay are inseparable. You're not seeing the field as it is. You're seeing a time-sliced version of it. Now discard the analogy. We do not reuse it. In the real universe, there is no single moment when light turned on, but there is a beginning of expansion, a finite age. The universe has not existed forever. That alone is enough to impose a hard observational limit. This means something unsettling but precise. There are regions of the universe that exist right now whose light will never reach us, not because it is blocked, not because it is too faint, but because space itself is expanding in such a way that the light is carried away faster than it can travel toward us. This is where intuition usually collapses into confusion, so we stabilize it carefully. The expansion of the universe does not mean galaxies are flying through space away from us like debris from an explosion. It means that the space between galaxies is stretching. As light travels through that space, the distance it must cross can increase faster than the light can compensate. So there are regions that were once observable, whose light reached us long ago, but whose current state is forever disconnected from us. There are also regions that have never been observable, and never will be. The observable universe is therefore not a snapshot of everything. It is a shrinking window into what can still communicate with us. And yet, when we see images of the observable universe mapped as a sphere around Earth, our intuition reasserts itself. It looks like a boundary, a bubble, a complete shape. The language reinforces the illusion the edge of the universe, the farthest objects we can see. But there is no edge in space. There is only an edge in time. At this point, we can state something clearly without exaggeration. The universe is almost certainly much larger than the observable universe, not slightly larger, not moderately larger, larger in a way that makes the observable universe a local sample, not a container. We know this not by seeing beyond the boundary, but by understanding how the boundary is created. It is not a physical limit, it is a consequence of cosmic history and finite speed. This distinction matters because it forces us to abandon a deeply rooted assumption that seeing more means approaching completeness. In the universe, seeing more only means reaching older light. As we go deeper, we will need to separate three things that intuition tends to merge: what exists, what can be observed, and what can be inferred. For now, we hold on to one stable conclusion. The universe you can observe is not the universe you live in. It is the part of it that has had time to announce itself. Once we accept that observation is limited by time, the next intuition that begins to fail is the idea that space itself is stable. We tend to imagine distance as something fixed, like the length of a road or the width of a room. Objects may move through space, but space itself feels passive, empty, merely a container. This assumption is so deeply embedded that we rarely notice it. When we say something is far away, we mean that the space between here and there is large, but static. We imagine that if we could travel fast enough, we could eventually cross it. Distance, in this view, is an obstacle but not a moving one. That intuition works perfectly well on Earth. It even works inside the solar system. It continues to work when we compare nearby stars. Nothing in those experiences forces us to imagine space changing underneath us. But the universe does not cooperate with this assumption. When astronomers began measuring distant galaxies carefully, they noticed something that did not fit the picture of static space. The farther away a galaxy was, the faster it appeared to be moving away from us. This was not a subtle trend. It was systematic. Distance and recession were linked. At first, this sounded like motion. Galaxies flying outward, an explosion, a center. This interpretation felt natural because it preserved our intuition. Objects move. Space stays still. But this explanation breaks down quickly. There is no center. Every observer, in every galaxy, sees roughly the same pattern. Everything else appears to be moving away, with speed proportional to distance. This is not how motion through space behaves. It is how expanding space behaves. We need to slow this down carefully, because the distinction matters. When space expands, galaxies are not travelling through space away from us in the usual sense. Instead, the space between galaxies is increasing. Distances grow even if the galaxies themselves are not actively moving. This is difficult to visualize because there is no everyday analogue that survives intact. Any analogy we try will break if pushed too far, so instead, we rely on repetition and constraint. Consider two galaxies separated by a certain amount of space. As the universe expands, that space stretches. Light travelling through it must cross more distance than before. The farther away a galaxy is, the more expanding space lies between us and it. The expansion accumulates. This accumulation is why distant galaxies recede faster, not because they are speeding up through space, but because there is more expanding space involved. Now we anchor this to observation. When light travels through expanding space, its wavelength is stretched along with that space. This stretching shifts the light toward longer wavelengths, redder light. This is called redshift. It is not a guess, it is measured directly. Redshift increases with distance. Distance correlates with expansion. Expansion correlates with time. These are not separate effects. They are the same process seen from different angles. At this point, intuition often tries to recover by imagining expansion as something that happens out there, beyond galaxies, while local space remains unaffected. This is partly true, but not in the way intuition wants. On small scales, gravity holds things together. Atoms, people, planets, galaxies themselves are not pulled apart by expansion. The effect is too weak compared to local forces, so your body does not expand, the solar system does not expand, the Milky Way does not expand internally. But between galaxies, where gravity is weaker and distances are enormous, expansion dominates. Over billions of years, it reshapes everything. This leads to a critical realization. Expansion is not something that happened once in the past. It is happening now, quietly, everywhere that gravity is not strong enough to resist it. So the universe is not just large, it is actively becoming larger. Now we combine this with what we already understand about observation. Light takes time to travel. Space expands while light is in transit. This means that the distance light must cross is not fixed during the journey. It increases. For nearby objects, this effect is negligible. The travel time is short, the expansion during transit is tiny. For extremely distant objects, the effect dominates. Light begins its journey across a certain distance, but by the time it arrives, the universe is much larger. The starting point is now far beyond where it once was. This is why we must be precise with the language. When we say a galaxy is a certain number of light years away, we are compressing a complex history into a single number. That number depends on how we define distance at emission, at reception, or something averaged in between. Our intuition wants one distance. The universe offers several, none of which behave like roads or lines. This matters because it reveals another quiet failure of intuition. We assume that if something is far enough away, it is simply harder to reach, not fundamentally unreachable. Expansion breaks that assumption. There exists a distance beyond which galaxies recede from us faster than light, not because they are moving through space faster than light, but because space itself is expanding. This does not violate relativity. It is built into it. Light emitted from beyond this boundary can still reach us if it started long ago, when the universe was smaller and the expansion rate different. But light emitted now, from those same regions, will never arrive. The space in between grows too quickly. This defines what is called a cosmic event horizon, not an edge, not a wall, a limit on future communication. So now we hold three constraints at once. The universe has a finite age, light has a finite speed, space itself expands. Together, these impose limits that no technology can bypass, not better telescopes, not faster travel, not patience. We can only observe what has already had time to reach us. We can only ever receive signals from a finite region, and that region changes with time. This leads to a conclusion that feels counterintuitive but unavoidable. The observable universe is not growing in the way we might expect. Although light continues to arrive from distant regions, the accelerating expansion of space means that fewer and fewer regions remain in causal contact with us. In the far future, the many galaxies we see today will fade from view, not because they disappear, but because their light can no longer overcome the expansion. The universe will not become emptier, it will become quieter. At this stage, it is important to restate what we now understand. The universe is not a static container filled with objects. Distance is not a fixed measure. Observation is constrained by time and expansion together. We have not yet said anything about how big the universe actually is. We have only established that the part we can observe is defined by limits that have nothing to do with the total extent. The failure of intuition here is complete but calm. The universe is not hiding its size from us out of malice or mystery. It is simply structured in a way that makes completeness inaccessible. As we continue, we will stop treating the observable universe as a proxy for the whole and begin treating it as what it is: a local, time-delayed, expansion-filtered sample of something much larger. Once we stop treating the observable universe as a container and begin treating it as a sample, a new intuition quietly asserts itself. We assume that even if we cannot see everything, we can still infer the shape of the whole from the part we observe. This is how we reason about most things. A shoreline curves, we infer a bay. A horizon bends, we infer a planet. This intuition feels careful, even scientific. We're not claiming to see everything, we're claiming to extrapolate responsibly. But this intuition also fails, and it fails for a reason that is not immediately obvious. To understand why, we need to talk about geometry not as a mathematical abstraction, but as a physical property of space itself. On Earth, geometry feels absolute. Parallel lines stay parallel. Triangles add up to 180 degrees. Circles behave predictably. This works because Earth is small compared to the scale at which curvature matters. Over short distances, a curved surface looks flat. The universe confronts us with the opposite situation. We're confined to a small region of an enormous structure. Our measurements are local. Our conclusions must be global. This inversion is where intuition becomes unreliable. When cosmologists talk about the shape of the universe, They are not asking whether it has an edge or a boundary. They are asking how space behaves over very large scales. Is it positively curved, like the surface of a sphere? Is it negatively curved, like a saddle, or is it flat? These words are dangerous because they carry everyday imagery that breaks under pressure, so we proceed carefully. A positively curved universe would eventually loop back on itself. Travel far enough in one direction, and you would return to your starting point. A negatively curved universe would expand away from itself faster than Euclidean intuition expects. A flat universe would follow the geometry you learned in school, extended indefinitely. The key point is this: all three possibilities can look the same locally. If you stand on a sphere large enough, the surface looks flat, the horizon appears straight, triangles look normal. Curvature only reveals itself when you measure across large enough distances. Now we connect this directly to the observable universe. The observable universe has a finite size, not because the universe is finite, but because of time and expansion. This means all of our geometric measurements are confined to a limited region, a very large region by human standards, but still a region. So when we measure the geometry of space, we are measuring the geometry of our observable patch, not the whole. This distinction is subtle but critical. Cosmologists have measured the geometry of the observable universe with extraordinary precision. They use patterns in the cosmic microwave background, the distribution of galaxies, and the behavior of light over vast distances. These measurements tell us that space, within our observable region, is very close to flat. Not exactly flat, but close enough that any curvature must be extremely small on the scales we can observe. Here is where intuition tries to leap to a conclusion. If the universe looks flat where we can see it, then perhaps it is flat everywhere. Perhaps it is infinite. This conclusion is tempting because it simplifies everything. Flat space extends naturally, no looping, no closure, just more of the same. But this inference is not logically forced. A sphere looks flatter the larger it is. If the universe is positively curved but vastly larger than the observable region, then our local measurements would still register near flatness. The same is true for other geometries. So the measurement space is flat does not mean space is infinite. It means curvature, if it exists, is on scales larger than what we can observe. This is not a weakness of measurement. It is a consequence of limited access. We can now state something carefully and precisely. The universe may be infinite. The universe may be finite but unbounded. The universe may have a global structure completely unlike the observable region. All of these are consistent with current observations. What matters for our intuition is not which option is correct, but why none of them can be ruled out by observation alone. Our intuition wants edges, it wants closure, it wants the universe to either end somewhere or repeat predictably. Geometry at cosmic scale does not offer that comfort. Instead, we are confronted with a situation where local information does not determine global structure. To anchor this, we restate the constraint. We are embedded inside the universe. We observe from one location. We receive information only via light. Light has travelled for a finite time. This means we never observe a completed shape. We observe a growing cross-section through time. Imagine trying to infer the shape of an entire forest by looking through a narrow clearing while the forest itself is growing. No matter how carefully you measure the trees you see, the unseen structure can remain radically different. Discard the analogy. The real universe offers no privileged vantage point. There is no external perspective from which the whole shape is visible. Every observer is limited in the same way. This leads to an important separation we must keep intact going forward. Observation tells us about the observable universe. Models tell us how that region behaves. Inference suggests how the whole might behave. These are not the same thing. The failure of intuition comes from merging them. When we say the universe is flat, we are making a statement about measured geometry within limits. When we say the universe is infinite, we are extending that statement beyond what observation can confirm. This does not make the extension unreasonable. It makes it conditional. At this point, it is important to address a quiet assumption that often goes unnoticed. We tend to think that if the universe were finite, we would notice something unusual near the end, a boundary, a distortion, a signal. But a finite universe does not require an edge. A sphere has no edge. Neither does a torus. Neither do many possible topologies. So the absence of an observed edge tells us nothing about finiteness. What we are left with is a universe whose global size and shape are underdetermined by observation. This is not a failure of science. It is a statement about what information is physically accessible. We can now stabilize the intuition again. The observable universe is large, but it is not representative of the whole by default. Its geometry appears flat, but that flatness does not constrain the total size. Its contents follow uniform laws, but uniformity does not imply completeness. The universe is not hiding its full extent behind a veil. The veil is built into time, light, and expansion. As we proceed, we will stop asking how far the universe goes and begin asking what it means for how far to even apply, because the concept of size itself is already under strain. By now, we have stripped away several comfortable assumptions. The universe is not limited to what we can see. Space is not static. Geometry does not reveal the whole from the part. Yet one intuition often survives all of this, that the universe, whatever its total size, must at least be describable as a single thing. One object, one connected expanse that simply extends farther than our reach. This intuition feels modest. We are no longer insisting on edges or centers. We are only insisting on unity. But even this assumption begins to fracture when we examine what expansion actually implies over long periods of time. So we slow down again. The expansion of the universe is not uniform in its effects. It does not merely increase distances. It changes which regions can influence each other at all. Over time, expansion reorganizes the universe into regions that are causally connected and regions that are not. Causally connected means that events in one region can, in principle, affect another by light, gravity, or any signal allowed by physics. If no signal can ever travel between two regions, they are causally disconnected. This is not an abstract distinction. It has direct consequences for what one universe even means. Earlier, we introduced the idea of a cosmic event horizon, a boundary beyond which events occurring now will never affect us. This horizon is not static. It evolves as the universe expands, and its existence implies something unsettling but precise. There are parts of the universe that are not just unseen, but permanently uncommunicable. To anchor this, we repeat the logic carefully. Light has a maximum speed. The universe expands. Expansion can increase distance faster than light can close it. When this happens, causal contact is broken. Now we add one more ingredient: acceleration. The expansion of the universe is not slowing down. It is speeding up. This acceleration is driven by something we call dark energy, not as an explanation, but as a name for an observed effect. Space expands faster now than it did in the past, and it will expand even faster in the future. This acceleration tightens causal limits. As time passes, more regions slip beyond our event horizon. They do not vanish. They simply stop being part of our causal network. So when we talk about the universe, we must be careful. Are we referring to all of space, regardless of connectivity, or are we referring to a causally connected region? Our intuition usually merges these without noticing. But physics does not. In practice, the universe fractures into vast domains that cannot exchange information. Each domain follows the same physical laws, but they evolve independently. This does not require speculation about multiple universes. It follows directly from expansion and finite signal speed. The observable universe is one such domain. It is not unique in principle. It is only unique by location. To prevent intuition from slipping into metaphor, we stay grounded. There is no wall separating these domains, no barrier, no boundary you could approach. The separation is temporal and dynamical, not spatial in the usual sense. If you were in a distant region beyond our horizon, your local universe would look much like ours. You would see galaxies. You would infer expansion. You would define your own observable universe centered on you. From your perspective, we would be part of the unreachable region. This symmetry matters. It tells us that our situation is not special. The universe does not privilege our location. Now we address a common recovery attempt by intuition. It might seem that if regions cannot interact, then talking about them as part of the same universe is meaningless. Perhaps the universe should be defined only as what is causally connected. This definition feels tidy, it restores unity, but it is arbitrary. The laws of physics do not change across these regions. The expansion history links them. Their separation is a result of evolution, not origin. They were once closer, once causally connected. The fragmentation is not primordial, it is emergent. This means that the universe as a whole can be connected in its past even if it is disconnected in its future. This temporal asymmetry matters deeply. Early in cosmic history, regions now beyond our horizon were close enough to exchange information. This is not an assumption. It is required to explain the observed uniformity of the cosmic microwave background. Distant regions share nearly identical properties because they were once in contact. As the universe expanded and accelerated, those regions drifted apart faster than signals could follow. So the universe does not begin fragmented, it becomes fragmented. This is where intuition must be rebuilt carefully. We tend to imagine the universe as a fixed stage on which things happen. Expansion suggests something else. The stage itself changes, and in doing so, it reshapes what together even means. Unity in space does not guarantee unity in interaction. At this point, it is useful to restate what we know without extrapolation. There exists a region we can observe. There exist regions we cannot observe now. There exist regions that we will never observe. All of these regions are governed by the same physics. All of them emerge from a shared early state. Many of them are no longer causally connected. This is not a philosophical statement. It is a structural one. Now we confront a deeper intuition failure. We often think of size as something absolute. Larger means containing smaller. A bigger box contains a smaller box. A larger region contains a smaller region. But causal structure does not follow this nesting intuition. A region can be part of a larger whole without being able to interact with most of it. Containment does not imply access. So when we ask how large the universe is, we are asking a question that mixes geometry with causality, and those two do not scale together. The total universe could be finite or infinite. That question remains open, but regardless of the answer, the portion that behaves as a single, communicative system is limited and shrinking. This forces a reframing. The universe is not just large in extent, it is large in disconnection. This does not make it chaotic. It does not make it unknowable. It makes it structured in a way that human-scale intuition was never designed to handle. We stabilize again. The universe we study is not a bubble floating in emptiness. It is a region defined by time, expansion, and causal reach. Beyond it, there is more not necessarily different, not necessarily exotic, but inaccessible. As we move forward, we will stop treating the unseen universe as a distant continuation and begin treating it as something fundamentally out of contact, because that shift is required to understand just how much larger the universe may be than anything we can ever observe. Up to this point, we have been careful not to speculate beyond what structure forces upon us. We have followed observation, expansion, geometry, and causality. Now a different intuition quietly enters, one that feels more technical and therefore safer. We assume that even if the universe is far larger than what we can observe, its large-scale behavior must be simple, uniform, smooth, governed by averages. This intuition is reinforced by what we see. On the largest observable scales, matter appears evenly distributed, galaxies cluster, but those clusters average out. No preferred direction, no obvious large-scale pattern. The universe looks statistically the same no matter where we look. This observation is so central that it has a name, the cosmological principle. It states that, on large scales, the universe is homogeneous and isotropic, the same everywhere, the same in every direction. This principle works extraordinarily well within the observable universe. It allows us to build models. It allows us to calculate expansion. It allows us to connect theory to measurement. But here is where intuition slips again. not because the principle is wrong, but because of how far we extend it. We quietly assume that if the universe is smooth here, it must be smooth everywhere. If the laws are uniform here, they must be uniform across all of space. If expansion behaves this way here, it must behave this way globally. This assumption feels conservative. It minimizes complication, but it is still an assumption. To see why, we need to understand what the cosmological principle actually rests on. It is not derived from first principles, it is inferred from observation, specifically from observing that the universe looks similar in all directions from our location, and from the assumption that we are not in a special place. That last part matters. The principle depends on what is called the Copernican assumption that our location is not privileged. We do not occupy a special position in the universe. Therefore, what we observe locally should be typical. This assumption has served science well. It displaced Earth from the center of the solar system. It displaced the Sun from the center of the galaxy. It displaced our galaxy from any cosmic center. But here, it reaches a limit. We only observe one region, one observable universe. We do not sample many. We do not compare across disconnected domains. We infer typicality from a single data point. This is not a flaw in logic. It is a limitation of access. To anchor this, we restate the structure. We observe that the universe is smooth on large scales within our horizon. We assume this smoothness extends beyond our horizon. We build models that require that extension. The models work, they predict observations accurately, this builds trust. But none of this proves that the universe beyond our horizon must share the same properties. It only shows that assuming it does leads to successful predictions here. This distinction is subtle but essential. At this point, intuition tries to stabilize by imagining the unseen universe as a simple extension. More galaxies, more space, more of the same. This is a reasonable working assumption, but it is not forced by observation. There exist cosmological models consistent with known physics, in which the universe is homogeneous on observable scales, but wildly different on much larger ones. The transition scale can be arbitrarily large, far beyond what we can observe. In these models, smoothness is local, not global. This does not mean such models are correct. It means they are not excluded. Now we introduce a constraint that sharpens the issue. Inflation. Inflation is a period of extremely rapid expansion that occurred very early in the universe's history. It explains why the observable universe is so smooth, flat, and uniform. Tiny regions were stretched enormously, smoothing out irregularities. Inflation is not introduced to speculate about unseen regions. It is introduced because it solves concrete problems within the observable universe. Horizon problems, flatness problems, structure formation. But inflation has consequences that extend beyond what we can observe. During inflation, space expanded exponentially. Regions that were once microscopically close were driven far apart. Many of those regions are now permanently causally disconnected. This means that inflation does not merely enlarge the universe, it fragments it into enormous domains. Within each domain, conditions can be nearly uniform. Between domains, conditions can differ. This is where intuition must be handled with care. We're not talking about different laws of physics. We're talking about different realizations of the same laws under different initial conditions. Small quantum fluctuations during inflation can be magnified into large-scale differences. Within our observable region, those fluctuations are small. Beyond it, they may not be. So when we imagine extending the smoothness, we see outward indefinitely. We are assuming that inflation behaved uniformly everywhere, and that fluctuations averaged out globally. But inflation does not guarantee that. It guarantees local uniformity. It does not guarantee global simplicity. Now we stabilize again. We are not claiming that the universe beyond our horizon is chaotic or exotic. We are claiming that observation does not constrain it. Uniformity here does not imply uniformity everywhere. This matters because it undermines another intuition that the observable universe is a fair sample of the whole. It may be, it may not be. We cannot know from observation alone. At this point, we separate carefully what is observed, what is modelled, and what is inferred. We observe large-scale uniformity within our horizon. We model this using homogeneous cosmologies. We infer that the same may hold beyond, because it simplifies and works locally. But the inference remains conditional. This does not weaken cosmology, it clarifies its scope. The universe may be vastly larger than the observable region and still obey the same physical laws, but its global structure, its total size, its total uniformity, its total topology can remain unconstrained. This leads to a critical recalibration of intuition. Bigness is not just about extent, it is about the number of independent regions that evolve without mutual influence. Inflation allows that number to be enormous, possibly infinite. So when we say the universe is big, we are not just saying there is more space beyond what we see, we are saying there may be vastly more independent realizations of cosmic history. Not different universes, the same universe disconnected by expansion. We hold this carefully, without dramatization. The observable universe is smooth. The universe as a whole may not be uniformly smooth. Observation cannot decide this. As we move forward, we will confront the consequences of this limitation directly, because once we accept that our observable region may not be representative, the idea of measuring the universe's total size becomes something fundamentally different from measuring distance. Once we accept that the observable universe may not be representative of the whole, a final intuition about size quietly collapses. We assume that if the universe is larger than what we can observe, then larger must still mean something measurable in principle, that there exists, somewhere, a total size perhaps unreachable, but conceptually well defined. This intuition feels disciplined. It does not insist on access. It only insists on definition. But this, too, fails under pressure. To see why, we need to separate two ideas that intuition usually merges: extent and meaning. A thing can extend farther without its total extent being a physically meaningful quantity. On Earth, size always has meaning, a continent has an area, an ocean has a boundary. Even if we cannot traverse it, we can define it. These definitions work because Earth exists inside a larger static framework. Space, time, and geometry are already in place. The universe does not sit inside anything. This is not a philosophical claim, it is a physical one. There is no external reference frame, no outside ruler, no background space relative to which the universe has a size. So when we ask how large the universe is, we are not asking the same kind of question we ask about ordinary objects. Now we slow down and rebuild carefully. In cosmology, distance is defined internally. It is measured between events, not against an external grid. These distances depend on the expansion history of the universe. They depend on time. They depend on how space itself behaves. This already tells us something important. There is no single, timeless answer to how big is the universe. The answer depends on when and how you measure. Within the observable universe, we can define distances operationally, light travel time, redshift, angular size. These give us consistent results because they are anchored to observation. But beyond the observable universe, none of these tools apply. There are no signals, no shared clocks, no synchronized rulers. So even if the universe extends far beyond what we can observe, its total extent may not be a quantity that physics can meaningfully assign. This is not a limitation of imagination, it is a limitation of operational definition. At this point, intuition tries to recover by appealing to mathematics. Even if we cannot measure it, surely we can define a total size mathematically. Sometimes we can, sometimes we cannot. If the universe is spatially infinite, then total size is not a number, it diverges. Asking how big it is becomes like asking how long the number line is. If the universe is finite but unbounded, like the surface of a sphere generalized to higher dimensions, then its total volume is well defined mathematically. But that volume depends on global properties we cannot measure. Curvature on scales larger than our horizon determines it. And if inflation continues indefinitely in some regions, a possibility allowed by current physics, then the total volume of the universe grows without bound. Not just large, unbounded in time. In such a case, the universe does not merely have a large size, it has no final size at all. This is where intuition must be rebuilt, not stretched. We are used to thinking of size as a property something has. The universe challenges this. Size becomes a process, not a static attribute. The universe does not simply exist at a given size, it grows, and depending on its global behavior, that growth may never converge to a total. Now we stabilize again by grounding this in what we know. We know the universe has been expanding for billions of years. We know that expansion is accelerating. We know that inflation likely occurred early on. From these facts alone, it follows that defining a total size may not be possible, even in principle. This is not because the universe is mysterious. It is because the concept of size assumes a completeness that the universe does not provide. Now we address another intuition that often lingers. We tend to think that if something cannot be measured, it is speculative or meaningless. But in physics, unmeasurable does not mean unreal. It means disconnected from operational access. The interior of a black hole beyond the event horizon is real, but unmeasurable from outside. The early universe before certain epochs is real, but indirectly accessible. The total extent of the universe may be real, but undefined in a way that measurement can capture. This is not a failure of science, it is a recognition of domain. We now restate what has changed in our understanding. Earlier, bigger than observable meant farther away. Now, it means beyond definable reach. The universe may be larger not just in distance, but in structure, in history, in number of independent regions, and in extent that never settles into a total. This leads to a subtle but crucial point. When cosmologists talk about the universe being at least a certain size, they are not placing a lower bound on a known quantity. They are stating the minimum extent required by observation, without implying that the total is finite or even well-defined. At least does not point toward a hidden number. It points toward the collapse of the question. The universe is larger than what we can observe. That statement is true. The universe has a total size we could someday know. That statement may not even be meaningful. At this stage, intuition often feels unsteady, so we slow the pacing and rest. We are not lost. We have simply reached the edge of what certain concepts can do. Size works well for objects inside the universe. It works less well for the universe itself. This distinction is not optional. It is forced by the structure of space-time. As we continue, we will not try to rescue the idea of total size. Instead, we will examine what replaces it, what cosmologists actually mean when they talk about how big the universe is, once size stops behaving like a number. Because the universe is not just larger than we can observe, it is larger than our usual categories can contain. At this point, we no longer treat size as a number waiting to be discovered. That intuition has been dismantled carefully. What replaces it is something less familiar but more stable structure. When cosmologists speak precisely about a universe larger than what we can observe, they do not describe it by how far it goes, but by how it is organized. This shift is easy to miss because everyday language resists it. We ask how big when we really mean how structured. So we slow down and make the transition explicit. The universe is described not by its total extent, but by the rules that govern how regions relate to each other: expansion rate, geometry, energy content, causal connectivity. These are not measurements of size, they are constraints on behavior. Once these constraints are specified, many different total universes become possible, some finite, some infinite, some growing without bound, all consistent with the same local observations. This is not ambiguity. It is degeneracy. Multiple global structures produce the same local outcomes. Our intuition wants to break this degeneracy. It wants a single answer, but physics does not require one. Now we confront a deeper intuition failure, the idea that knowing the laws of physics should determine everything. We tend to believe that once the laws are known, the universe becomes fixed. Initial conditions are set. Outcomes follow. The total structure should be derivable. This belief is reinforced by success in smaller systems. If we know the laws governing a pendulum and its starting position, we can predict its motion. If we know the laws of gravity and initial orbits, we can predict planetary motion. But the universe is not a subsystem. It has no external boundary conditions imposed from outside. The laws of physics tell us how regions evolve, not how many regions exist. This distinction matters. Physical laws describe relationships. They do not specify total content. So even with a complete understanding of physics, as complete as that idea can be, we may still not be able to say how many causally disconnected regions exist, how far the universe extends, or whether that extension ever terminates. This is not because the laws are incomplete. It is because they do not ask that question. At this stage, intuition often tries to recover by introducing probability. If we cannot know the total size, perhaps we can assign likelihoods. Perhaps one structure is more probable than another. But probability requires a measure, a way to count possibilities, and this is where another limitation appears. In cosmology, defining probabilities over infinite or unbounded structures is notoriously difficult. If the universe is infinite, then every allowed configuration occurs infinitely many times. Counting becomes meaningless. Ratios diverge. Normalization fails. This is not a technical inconvenience. It is a structural problem. So when we ask how likely a given global structure is, we quickly discover that the question itself may not be well posed. Once again, intuition wants a number. Physics offers a framework. Now we stabilize by returning to what is solid. We can describe the observable universe in detail. We can model its evolution with high precision. We can test these models against observation. All of this works without requiring knowledge of the total. The failure of intuition is not that we cannot know everything. It is that we assumed everything needed to be known to understand our situation. We do not need to know the total size of the universe to understand expansion, structure formation, or cosmic history within our domain. This reframing matters because it shifts what bigger than observable actually implies. It does not mean the same thing, continued outward. It means a system whose global properties are underdetermined by local data. Now we make this concrete by examining what cosmology actually measures. Cosmologists measure parameters: the density of matter, the density of radiation, the density associated with dark energy, the curvature of space within the observable region, the spectrum of initial fluctuations. These parameters define a class of universes, a family. Within that family, there exist many possible global realizations. Our universe is one member of that family. The observable region is one patch within that member. This hierarchy is easy to state but hard to internalize. We are not measuring the universe directly. We are measuring our patch. We infer a model. That model allows many total universes. The intuition failure comes from collapsing these levels into one. Now we address a subtle concern. It may seem that if the total universe is underdetermined, then statements about it are arbitrary. But this is not the case. There are constraints. Not everything is allowed. The universe must be consistent with known physics. It must have evolved from an early state compatible with inflationary dynamics. It must allow for the observed uniformity and structure. It must obey conservation laws. These constraints eliminate vast classes of possibilities. They do not, however, isolate a single global structure. So when we say the universe is far bigger than what we can observe, we are not gesturing vaguely. We are making a precise statement about underdetermination. There exist global properties that no amount of observation within our horizon can fix. This is not unique to cosmology. It appears in other areas of physics as well. Local measurements do not always determine global topology. Fields can have configurations that differ globally while agreeing locally. The universe simply takes this to an extreme. Now we rest again. We have not lost rigor, we have gained clarity. The universe's largeness is not just about distance or volume, it is about freedom. Freedom in how much exists beyond what we can access. As we continue, we will examine the strongest known mechanism that exploits this freedom inflation pushed to its logical limit. Because inflation does not merely allow the universe to be large, it allows it to be incomprehensibly larger than any single region can ever reveal. When inflation is treated as a local event, it already stretches intuition. But when we follow its logic without interruption, it forces a far more radical conclusion, one that directly reshapes what bigger than observable actually means. So we proceed carefully, without introducing anything new prematurely. Inflation, at its core, is a period during which space expanded extremely rapidly. Driven by a high-energy state of the universe, this expansion was not gradual, it was exponential. Distances did not simply increase, they multiplied repeatedly in very short intervals. Within the observable universe, inflation explains several things cleanly. It explains why space appears nearly flat. It explains why distant regions share similar properties. It explains why tiny quantum fluctuations became the seeds of galaxies. All of this remains within familiar scientific territory. The critical shift happens when we ask a simple, restrained question: did inflation happen everywhere in the same way, and did it ever fully stop? To answer this, we do not speculate, we follow what the models themselves allow. In many inflationary models, inflation does not end everywhere at once. Instead, it ends locally. In some regions, the high-energy state decays, inflation slows, and a universe like ours begins to form. In other regions, inflation continues. This is not an exotic add-on, it is a generic feature of how these fields behave. So inflation becomes a process, not an event. Some regions exit inflation and form hot, expanding universes filled with matter and radiation. Other regions continue inflating, expanding even faster, creating more space between all regions. This leads to a structure that intuition is not prepared for. The universe does not inflate once and settle. It inflates continuously in many places. Regions like ours are pockets, local outcomes within a much larger ongoing process. This is often described as eternal inflation. The name can mislead, so we strip it down to its mechanics. Eternal does not mean infinite in the past. It does not mean unchanging. It means that inflation never ends everywhere. At any given time, there exist regions where inflation has ended and regions where it continues. As long as some regions keep inflating faster than others stop, the total inflating volume grows. This has a precise consequence. The total volume of the universe increases without bound. Not eventually large, not asymptotically approaching a size, unbounded. Now we pause, because intuition will attempt to resist this. It may try to imagine an extremely large but finite universe. It may try to imagine inflation as something that mostly finished. It may try to restore a final size. The models do not allow that recovery. As long as inflation continues somewhere, new regions are constantly being created that are forever out of causal contact with existing ones. These regions are not elsewhere in space. They are separated by expansion that outruns communication. So the universe is not just larger than the observable universe, it is larger in a way that does not settle into a total. This is where earlier distinctions become necessary. We separated observable from unobservable. We separated causally connected from disconnected. We separated local laws from global structure. Inflation ties these together. Each region where inflation ends becomes its own causally connected domain. Within that domain, physics unfolds, galaxies form, observers could arise. Each domain has its own observable universe. These domains are not sequential, they coexist. From within any one of them, the others are not just unseen, they are unreachable in principle. Now we stabilize the intuition again. We are not multiplying universes arbitrarily. We are following one universe whose expansion history creates many independent regions. The universe remains one physical system, it just does not behave as one communicative system. This distinction is essential. At this point, we can state something carefully. If inflation is eternal, then the universe is not just larger than the observable universe, it is larger than any finite collection of observable universes. No matter how many domains you include, there are more forming. This is not a claim about infinity for dramatic effect. It is a statement about process without global termination. Now we address a common intuition failure. It might seem that if the universe contains infinitely many regions like ours, then everything that can happen will happen, infinitely many times. This conclusion is often stated casually, but it requires careful handling. Whether this is true depends on the details of physical laws and initial conditions. Not everything imaginable is allowed, but many configurations may recur. What matters here is not repetition, it is scale. The scale is not just large, it is structurally unbounded. This reframes the original question entirely. How big is the universe no longer means how far does it go. It means, does the process that creates space ever end? If the answer is no, then size is not a static property. It is an ever-growing outcome. At this stage, we also confront the limits of confirmation. Eternal inflation is not directly observable beyond its local consequences. We infer it because it emerges naturally from models that already explain what we see. But we cannot watch other regions form. We cannot receive signals from them. So we separate again, explicitly. Observation. The observable universe shows signs consistent with inflation. Modelling many inflationary models predict eternal inflation. Inference the universe may therefore be vastly larger than any observable region. This inference is conditional, not absolute. But notice something important. Even if eternal inflation is false, even if inflation ended everywhere, everything we established earlier still holds. The universe can still be vastly larger than what we can observe. Its total size can still be undefined. Causal disconnection still occurs. Eternal inflation does not create largeness from nothing. It amplifies it. So the conclusion does not rest on one speculative idea. It rests on the cumulative structure we have built. Now we rest again. The universe may be finite or infinite. Inflation may be eternal or not. But in the strongest, well-motivated models we have, the universe is not just bigger than observable, it is larger in a way that defeats enumeration. As we move forward, we will not ask whether this picture is comforting or unsettling. We will ask something more precise. Given this structure, what can we legitimately say we know, and where do we encounter true, stable boundaries of knowledge? At this point, it would be easy to let the scale overwhelm the structure, so we pause deliberately and introduce a constraint that has been implicit all along discipline. We now need to separate what is known, what is inferred, and what remains fundamentally undecidable without allowing scale to blur those boundaries. This matters because when the universe becomes very large, larger than observation, larger than definition, larger than enumeration, intuition often collapses everything into speculation. That collapse is unnecessary. So we proceed methodically. We begin with what is directly observed. We observe that the universe is expanding. We observe that the expansion is accelerating. We observe a nearly uniform cosmic microwave background. We observe a specific spectrum of fluctuations. These are not interpretations, they are measurements. From these observations, we build models. The models introduce parameters, equations, and mechanisms that reproduce what we see. Inflation is one such mechanism. Dark energy is another. Geometry emerges from the equations of space-time. Models are not facts, they are tools. A model earns trust by explaining multiple observations with a single framework. Inflation earned that trust because it explains several otherwise unrelated features of the observable universe. Now we move one step outward. Some models imply consequences beyond what we can observe. Eternal inflation is such a consequence. It is not added to explain unseen regions. It emerges because the same dynamics that solve local problems do not naturally terminate globally. This is inference. Inference is not guesswork. It is extrapolation under constraint, but it is still distinct from observation. This distinction matters because it allows us to identify the true boundaries of knowledge without dramatizing them. We do not know whether inflation is eternal. We do not know the total extent of the universe. We do not know whether the universe is finite or infinite. These are legitimate unknowns, but they are not arbitrary unknowns. They are bounded. Not everything is unknown, not everything is possible. This is where intuition often misfires again. It may seem that once the universe becomes this large, science loses grip, that anything can be said. That evidence no longer matters. The opposite is true. As scale increases, constraints become more important, not less. We know the universe obeys specific physical laws. We know those laws have been tested extensively within our domain. We know that large deviations would have observable consequences. So while the total universe may be vast beyond reach, it cannot be wildly inconsistent with what we observe locally without leaving traces. This narrows the space of possibilities. Now we address a specific intuition failure, the idea that if something cannot be observed even in principle, it is meaningless to talk about it scientifically. This intuition is understandable, but it is incorrect. Physics often deals with unobservable entities. Quarks are confined. Space-time curvature cannot be seen directly. Wave functions are not observed, only their effects. What matters is not direct observation, but consistency, explanatory power, and indirect consequence. The unseen universe beyond our horizon does not influence us now, but it influences what kind of universe we inhabit by constraining how our region came to be. Inflationary dynamics, initial conditions, and global structure shape local outcomes even if the rest remains unreachable. So talking about the larger universe is not meaningless, it is just limited. Now we restate the deepest boundary we have encountered so far. There are questions whose answers cannot be obtained by accumulating more data within our horizon. No telescope, no experiment, no patience will reveal the total size of the universe or whether inflation continues elsewhere. These are not technical limits, they are structural limits. The universe has arranged itself in such a way that some global properties are forever hidden from any local observer. This is not failure, it is architecture. At this point, we need to stabilize the concept of we don't know, because it has been earned. We don't know. Here does not mean we haven't figured it out yet. It means the question cannot be settled by observation within our causal domain. That is a different category of unknown. Now we hold this boundary calmly. Beyond it, speculation exists. Within it, science remains precise. The mistake intuition often makes is to treat all unknowns as temporary. History encourages this. Many things once unknown became known, but not all unknowns are of the same type. Some are hidden by ignorance, and some are hidden by distance, some are hidden by structure. The total size of the universe belongs to the last category. Now we re-anchor. What do we actually know about the universe's largeness? We know it is larger than what we can observe. We know that the observable region is not privileged. We know that expansion creates causal disconnection. We know that inflation plausibly amplifies this disconnection enormously. This knowledge is stable. We do not know the total. We may never know the total. And yet, this does not weaken our understanding of where we are. At this stage, intuition often expects a collapse into abstraction. We resist that. We remain grounded. We live in a universe whose observable portion has a finite size, a finite age, and a well-defined history. That history is embedded in a much larger structure whose total properties are underdetermined. This is not an invitation to imagine endlessly. It is a constraint on imagination. As we continue, we will not expand scale further. Instead, we will return to something familiar and re-examine it under this rebuilt intuition. We will return to the observable universe not as a boundary, but as a working region, and ask what it means to live in a cosmos that is not just big, but structurally incomplete from any internal viewpoint. We return now to the observable universe, but not to shrink the picture. We return because our intuition about what it means to inhabit a region has changed. Earlier, the observable universe felt like a container everything that matters, bounded by distance. Now it must be treated as something else entirely, a working domain defined by limits, not by completeness. This shift is subtle, so we rebuild it slowly. The observable universe contains everything that has been able to affect us since the beginning of cosmic expansion. Every photon we detect, every galaxy we map, every background signal we analyze belongs to this region. It is coherent, it is internally connected. It is governed by the same physical laws throughout. In practical terms, it is the universe we can do science in. This is not a dismissal of what lies beyond. It is a recognition of operational reality. Within this domain, time, distance, and causality are linked in stable ways. We can trace cosmic history from early hot plasma to galaxies and stars. We can model structure formation. We can test predictions. The fact that the universe may be vastly larger than this domain does not diminish its scientific completeness as a region. This is where intuition often falters again. We're used to thinking that being a small part of something larger makes that part less meaningful. But in physics, regions do not lose coherence because they are embedded in larger structures. A laboratory experiment does not become invalid because the laboratory is inside a city. The city does not become invalid because it is on a continent. Containment does not dilute structure. Discard the analogy. The observable universe is not a subset in the everyday sense. It is a causally complete system. Everything that can influence us is already inside it. Everything outside is irrelevant to prediction, not because it is unimportant, but because it is disconnected. This distinction matters because it stabilizes our understanding. We are not missing pieces needed to explain what we see. We are missing access to parts that cannot affect what we see. That is a different kind of absence. Now we address a lingering intuition that if the universe is much larger than the observable region, then our location must be insignificant, or typical, or statistically negligible in some uncomfortable way. This intuition mixes scale with relevance. Physics does not care about typicality in the emotional sense. It cares about conditions. The observable universe has the conditions it has because of its history, not because of its rank among all regions. Whether there are many regions like ours or few does not change the laws governing ours. This is important because it prevents a subtle conceptual error. We do not need to know how many observable universes exist to understand this one. The existence of others does not alter our measurements. Now we turn to a more precise question. If the universe is far larger than observable, why does it appear so orderly here? The answer is not that we are in a special place. It is that only certain regions allow observers at all. Regions that are wildly irregular, or collapse too quickly, or fail to form structure, do not support long-term complexity. This is not a philosophical statement. It is a physical constraint. Structure requires time. Time requires expansion that neither tears matter apart too quickly, nor collapses it immediately. The observable universe satisfies these conditions. Whether many regions satisfy them or few is a separate question. What matters is that this region does. Now we stabilize again. The observable universe is not a random slice. It is a region with a specific expansion history and energy balance that allows complexity to emerge. This does not make it privileged. It makes it suitable. Suitability does not require rarity. It does not require design. It requires compatibility. Now we confront another intuition failure. It is tempting to think that if the universe is larger than observable, then cosmology must eventually dissolve into statistics over unseen regions, that our explanations become anthropic by necessity. This is not true. Within the observable universe, the evolution of structure follows physical laws that are testable and predictive. We do not explain galaxy formation by appealing to unseen regions. We explain it by gravity, matter content, and initial fluctuations. The existence of a larger universe does not replace these explanations. It contextualizes them. Now we restate what the observable universe actually gives us. It gives us a complete causal history from early times to now. It gives us a closed system for testing physical laws. It gives us enough information to reconstruct its past with confidence. It does not give us the total. This is not a deficiency. It is a boundary. At this stage, intuition often expects a kind of resignation, a sense that something essential is missing. We resist that tone. Nothing essential for understanding our cosmic history is missing. The early universe was hot and dense. It expanded and cooled. Tiny fluctuations grew into galaxies. Expansion accelerated. All of this is internally complete. The fact that the universe extends beyond this story does not change the story's coherence. Now we turn toward the ending by gently reframing the original question. We began by asking why the universe is far bigger than what we can ever observe. The answer is no longer a single mechanism or number, it is a layered structure. Finite age limits observation, expansion reshapes distance, acceleration enforces disconnection, inflation amplifies scale beyond reach. Each layer adds inevitability. The universe is not larger than observable by accident. It is larger because of how space-time itself behaves. Now we slow the rhythm again. We have rebuilt intuition step by step. We have removed the expectation of completeness. We have replaced size with structure. What remains is not uncertainty, but clarity. As we move to the final section, we will not introduce new ideas. We will return to the opening and allow the rebuilt intuition to settle, because the universe has not changed during this journey. Only our ability to stand inside its scale has. When we look outward now, nothing about the sky has changed. Stars still appear fixed. Galaxies still arrange themselves into familiar shapes. The visual experience remains calm and continuous. What has changed is how we understand what that experience represents. The night sky does not show us space as it exists now. It shows us a layered record of what has been able to reach us. Near objects are seen almost as they are. Distant objects are seen as they were. Very distant objects are seen as they were when the universe itself was young. This distinction no longer feels surprising. It feels structural. Light is not a messenger that travels through an unchanging arena. It moves through space that stretches while it travels. Every signal arrives having crossed a distance that did not remain fixed during its journey. This means that observation is inseparable from cosmic history. The farther we look, the more the universe forces us to trade presence for time. At the same time, expansion does more than stretch distances. It reorganizes what can ever be connected. Regions that were once close enough to exchange information drift apart faster than any signal can follow. Communication shuts down, not because of barriers, but because of the motion built into space-time itself. This is not a dramatic event. It does not announce itself. It accumulates quietly. As expansion accelerates, causal horizons harden. Information that has not already arrived never will. Regions do not disappear. They simply stop participating in the same network of cause and effect. So the observable universe becomes what it truly is, a complete causal domain, not a container of everything. Everything that has influenced our history is inside it. Everything outside it is irrelevant to prediction, not because it is unimportant, but because it is disconnected. This reframing is stable now. It does not feel like loss. The observable universe is not incomplete in the way a broken picture is incomplete. It is complete in the way a chapter is complete. It has a beginning, a structure, and a coherent internal logic. What lies beyond is not missing information. It is inaccessible information. That difference matters. We can trace the universe's history within this domain with confidence. A hot, dense beginning, rapid expansion, cooling, the formation of simple particles, then atoms, then stars and galaxies, the gradual emergence of structure, the recent onset of accelerated expansion. None of this depends on what lies beyond our horizon. The laws governing this evolution are tested and precise. They apply everywhere we can test them. Their consistency does not weaken because they may apply elsewhere as well. The universe being larger than observable does not undermine explanation. It clarifies its scope. There is no experiment we are failing to perform. There is no deeper observation waiting just beyond reach. The limits we encounter are not technological. They are built into time, light, and expansion. This is why the universe never appears to have an edge. There is no physical boundary to approach. There is only a limit on communication. The sky does not thin out. It does not signal incompleteness. It simply stops telling us about regions that have slipped out of causal contact. This is also why the idea of seeing farther eventually stops being meaningful. Seeing farther only means seeing older light. It does not mean approaching the whole. The universe does not gradually reveal itself with better instruments. It reveals its history, layer by layer, until history itself runs out. Beyond that point, there is still universe, but there is no signal. At this stage, intuition no longer reaches for completion. It no longer expects a final map. That expectation belonged to a world where space was static and access was unlimited. Here, access is the limiting factor. The universe is not withholding its size. It is structured so that size beyond a certain point cannot become part of any observer's experience. This does not make the universe unknowable. It makes knowledge local. Local does not mean small. The observable universe contains hundreds of billions of galaxies. It spans tens of billions of light years. It encompasses nearly the entire history of cosmic time. Local means causally closed. Within that closure, understanding is deep and reliable. Beyond it, structure may continue, expansion may continue, inflation may continue, or it may not. These are legitimate unknowns, clearly bounded by what observation can ever decide. We don't know here is not a temporary placeholder, it is a stable boundary. That boundary does not invite speculation, it invites precision about what questions make sense. Asking how large the universe is in total assumes that total is a property the universe offers. Everything we have learned suggests that it may not. What the universe offers instead is structure without completion, process without a final measure, laws without a global inventory. This is not unsettling once intuition adjusts. It is simply how space-time behaves when expansion, finite signal speed, and cosmic history are taken seriously. Now, when we say the universe is far bigger than what we can ever observe, the statement no longer feels vague. It means that no observer, anywhere, can assemble the whole into a single picture. Every observer inhabits a region that is complete in itself and incomplete in relation to the whole. This is not a special limitation of us. It is a general feature of the universe. From any location, the same constraints apply. Horizons form, expansion separates, history filters access. There is no privileged vantage point from which the universe appears finished. So the universe does not overwhelm us with size. It simply outgrows the concept of size as something observation can close. What remains is stable. We understand why the observable universe is limited. We understand why that limit is permanent. We understand why nothing essential for explanation lies beyond it. The universe has always been larger than what we can observe. The only change is that this no longer feels like a gap. It feels like the natural consequence of living inside space-time. Tonight, we began with something familiar, a universe filled with stars, galaxies, and distant light, a universe that feels large, but still imaginable. What has changed over the course of this descent is not the universe itself, but the frame we use to hold it. At the beginning, size felt like distance. Farther meant older. Bigger meant more. The universe seemed like a vast space waiting to be revealed with better tools and more time. Now that intuition has been replaced, we understand that when we look out into the universe, we are not surveying a space. We are receiving signals that have survived a journey through expanding space-time. What reaches us is determined not by how far we look, but by how long the universe has existed and how it has changed during that time. The observable universe is not a boundary drawn in space. It is a boundary drawn in history. This reframing settles quietly. It does not require drama or speculation. It follows inevitably from three facts we now hold comfortably together. Light takes time to travel, space expands, and expansion accelerates. From these alone, the universe becomes larger than observation allows. Not slightly larger, not temporarily larger, larger in a way that no increase in patience, technology, or ingenuity can overcome. This is why the phrase "the observable universe" now feels precise rather than provisional. It does not mean what we can see so far. It means what can ever be seen. Everything beyond it is not hidden behind darkness or distance. It is separated by the structure of space-time itself. We also understand now why this does not diminish what we know. The observable universe contains a complete causal history. It contains everything that shaped our past and everything that can influence our future. Its internal structure is coherent, testable, and deeply understood. Stars form, galaxies evolve, space expands, light stretches. These processes do not depend on what lies beyond our horizon. The universe does not become incomplete because it extends further. It becomes layered. Each observer, anywhere, inhabits a region like this one, a region that is complete from the inside and incomplete from the outside. No observer ever steps back far enough to see the whole. This is not a limitation of us, it is a universal condition. We also return now to the idea of scale, but in its rebuilt form. The universe is not far bigger than observable because it has a distant edge we cannot reach. It is far bigger because size itself stops behaving like a property that can be finished. Expansion turns distance into history. Acceleration turns history into separation. Inflation, if it occurred as our models suggest, turns separation into an unbounded process. At no point does the universe offer a final number. This is why asking how big is the universe no longer feels like an unanswered question. It feels like a misapplied one. What we can ask and answer is how the universe behaves, how regions relate, how structure forms, and how limits arise. Those questions lead to stable understanding. The universe is not withholding its total size. It is structured so that total size is not something an internal observer can acquire. Now we return fully to the opening. Tonight, we said we were going to talk about the universe you already recognize and why your intuition about its size fails. That failure is no longer confusing, it is expected. Your intuition evolved to navigate distances that remain fixed and environments that can be fully surveyed. The universe violates those assumptions quietly, without signaling the moment they break. What replaces intuition is not a new picture, but a new stance. We no longer imagine the universe as a thing we could someday finish mapping. We understand it as a process whose structure exceeds any single viewpoint. This does not leave us small or insignificant, it leaves us correctly placed. We live inside a universe whose accessible region is vast, ancient, and rich enough to contain everything we have ever observed and everything that has ever affected us. Beyond that region, the universe continues not as a mystery to be solved, but as a consequence of how space-time works. This is the reality we live in. We understand it better now, and the work continues.